Hello, everyone. Today we have Kefan Dong presenting some joint work with Tengyu Ma. And so Kefan is a third-year PhD student from Stanford University, and he's supervised by Tengyu Ma, and he received his bachelor's from Yao's class in Tsinghua University. And I guess, as we all know, he's interested in reinforcement learning theory, and today he'll be presenting about asymptotic instance-optimal algorithms for interactive decision-making. And just if you have any questions, put in the chat and I can direct that to Kefan, or if you want, you can just raise your hand and ask your question. So go ahead.
Thanks for the introduction, and thank you for organizing this wonderful seminar. So yeah, let's get started. Today I'm going to talk about asymptotic instance-optimal algorithms for interactive decision-making. And this is a joint work with my advisor, Professor Tengyu Ma. So let me start with some motivations for instance-dependent algorithms. So many of the classical machine learning algorithms and analysis focus on the worst-case instances. However, an ideal algorithm should perform better on easy instances, and this means that the regret or the error should depend on the instance. Now, we can visualize this thing in the following figure, where the x-axis denotes the instances, and the y-axis is the error or the regret of the algorithm. Now, the worst case bound just tries to find a single value that upper bounds the error or the regret across all the instances. So it is here a constant function in this figure. But for instance-dependent algorithms, the error or the regret depend on the instance, so we can see some small values on easy instances. So there are a lot of notable examples here for instance-dependent algorithms. For multi-unbounded and reinforcement learning, we can have a regret bound that depends on the gap or the value of the optimal policy. And for classical supervised learning, we can have an error bound that depends on the margin. However, when we try to compare these algorithms, there is a challenge. This is because for different instance-dependent algorithms, they may depend on different properties of the instance. So it is very likely that on some of the instances, one algorithm is better, but on other instances, a different algorithm is better. So it's unclear what algorithm should we choose if we don't have a very accurate prior on the instance we are working on. So now a way to get around this is to ask for a stronger guarantees for the algorithm, which is called instance-optimal algorithms. So we're interested in designing a single algorithm that can outperform all other algorithms on every instance. So if we look at the visualization here, we have, say, a lot of different instance-dependent algorithms. But if we can find an algorithm that is better than every one of them, then we're good. However, this thing is kind of too good to be true on the surface. This is because we can easily design an algorithm that perfectly memorize one special instance and fail on all other instances. So say you have a bandit problem, and you can have an algorithm that takes no samples and just directly commit to one particular action. Then this algorithm will have like zero regret on some instances, where the optimal actions coincides with the action you commit. But it will have linear regret on other instances. So the regret bound will look like this. And we can also have like different algorithms that overfits to different instances. It means that if we want to be better than any of these algorithms, we must have a zero regret on all the instances, which is clearly impossible. However, like comparing with this like overfitting algorithms are not very interesting. This is because those algorithms are can hardly be called like learning algorithms because they take no examples. So what we are interested is to compare with all other reasonable algorithms here. And by reasonable, we mean the algorithm shouldn't completely fail on any instance. So in particular for bandits and reinforcement learning, this seminal work by Lai and Robbins, they define reasonable to be achieving non-trivial regret on all instances. So mathematically speaking, an algorithm is called consistent if it achieves n to the p regret for every p bigger than 0 on every instance. This means we put an upper bound for the regret for every consistent algorithms. Then we can get rid of all the cheating algorithms. So at least we don't have a trivial counterexample for the existence of instance optimal algorithms. Meanwhile, this definition still includes some interesting algorithms such as UCB, because we know that when working on when treating the problem as a multi-arm bandit instance, UCB algorithm always have like log n regret. Then we say an algorithm is instance optimal if its regret is as good as every consistent algorithm on every instance. An interesting point here is that if we replace the n to the p regret upper bound by something like n to the 0.9 in the definition, we only affect some constant factors later in our analysis. So this definition of consistent algorithm is quite flexible. Okay, so there are lots of prior works on instance optimal algorithms for different settings. So we know that there are instance optimal algorithms for multi-arm bandit, linear bandits, contextual bandits, and I think also for structured bandits and ergodic Markov decision processes. Even though we only compare with reasonable algorithms, the existence of instance optimal algorithm shouldn't be taken for granted because presumably every algorithm has its own speciality on a subset of the instance. So it's unclear whether we can design a single algorithm that is better than every other consistent algorithm. So in this paper, somewhat surprisingly, we design instance optimal algorithms for general interactive decision-making problems with finite actions. And that includes episodic or like finite horizon Markov decision processes. We also derive the optimal rate of instance optimal algorithms. Okay, that's all for the motivation. I'll pause for questions here.
It seems everything is clear.
Okay,
it's clear
sounds
to
good.
me.
Thanks. Then, okay, let's move on. Let me first give a very quick overview of the interactive decision-making framework. So in this framework, we have an agent or the learning algorithm, and we also have a environment. So in each round of the interaction, the agent choose a decision pi sub t and send it to the environment. Then the environment generates a observation O sub t, and the agent receive a reward R of OT. So here we assume that the reward function is known and it is a deterministic function of the observation. This is still quite general because you can put every bit of randomness into the observation. And this whole process is repeated for n times. Now, this interactive decision-making framework includes reinforcement learning, POM DPs, contextual bandits, and multi-arm bandits, and many other settings. So for example, if we have a finite horizon reinforcement learning, our observation is the entire trajectory. So it's a collection of state, action, reward pairs. And in this case, the reward function is just a summation of all the reward in this trajectory. And an instance here corresponds to a particular environment. So for Markov decision process, an instance means a particular choice of the transition function as well as the reward function. And of course, our goal is just to minimize the regret, which is defined to be the summation over the reward of the optimal decision minus the reward of the decision selected by the agent. And as you can see that in this framework, we abstract away the structure of the problem by introducing this single random variable called observation. And this is actually, this abstract view actually helps us to simplify the analysis later. So let me give a quick overview of our main contributions. So we compute the exact leading term of the optimal asymptotic regret denoted by C of f log
Can
n.
I ask a clarification
Sure.
question? So you mentioned finite action earlier, but now you're talking about policies. What's the relationship between finite action and the policy space?
Oh, so yeah, in this paper, we just assume that the decisions or the policies are finite. So
A finite set of policies.
yeah. So for tabular
And
reinforcement learning, it's kind of always true because the policy
right,
is yeah,
right.
it's finite.
Okay, and in a way, yeah, it's like stochastic policies are like, okay, that's fine. Like you can take the convex combination of policies and then that's fine. But
Right.
going beyond that, you should have an infinite policy space. I see. Okay, good.
Yes.
Yeah,
Yes.
thanks.
Okay. Right. So in this paper, we just compute the form of the optimal asymptotic regret, C of f log n. So C of f here is the it's a complex measure that we introduce, and we can prove corresponding upper and lower bounds. So for lower bound, we say that on every instance f, the regret of every consistent algorithm must have the following form. So regret divided by log n is asymptotically larger than C of f. And we also design an algorithm that with mild conditions, its regret divided by log n is asymptotically smaller than C of f. And in this sense, this is the first asymptotic instance optimal algorithm for general interactive decision making.
Oh,
Okay. Yeah.
Quick question. I would
Go
have
ahead.
expected a lower bound limit. That would be stronger.
Yes, that would be stronger, but I think our current technique only proves limb soup.
Okay, interesting.
I'll
be curious to hear why. Okay, yeah, we can talk about it
yeah.
later.
Maybe we can talk about that offline. Yeah.
Okay.
Yeah.
I have another question.
Maybe that's first. Yeah, sure. Go ahead.
Yeah, the work of Andrew Wagenmaker, he also has something like related to this setting. Is that, how does that relate to this? I can't remember. Do you know of the work?
Which particular work are you talking
Oh,
about?
I think he recently shared like some also asymptotic results on interactive decision making.
Oh, do you mean that one with the non-asymptotic guarantees?
Yeah.
Oh, yeah. So, yeah, I think his work is more like focusing on the low order term to improve the low order terms. But the asymptotic part, like the leading term of the regret, should be the same.
Okay, so his constant here would be the same. The C
yes.
of F.
The C of F should be the same. Yeah. I'll touch on that later in this talk. Yeah. Okay. So before I move forward, let me introduce some additional notations. So we use the letter capital pi to denote the set of decisions, and we assume capital pi is finite. And we use capital F to denote the set of instances. And we use this notation f of pi to denote the distribution of observations if we execute the decision pi on the instance f. And we use r sub f of pi to denote expected reward of the decision pi on the instance f. So the optimal decision, of course, is the decision that maximizes the reward. And we make the assumption that the optimal decision is unique for every instance. I think this assumption is standard in prior works on asymptotic, prior works on instance optimality. Okay, now let me introduce our complexity measure and the intuition of the to design this complexity measure. So recall that C of F is actually a lower bound for the regret of every instance optimal for every consistent algorithm. So to design this lower bound, we just need to find some common ground for all the consistent algorithms. To this end, we look at let's use F to denote the true instance and G to be another instance with a different optimal decision. Then we claim that every consistent algorithm must distinguish G from F. Okay, why? This is because sublinear regret means that we must play on the optimal decision of F for most of the time if the true instance is F. And similarly, we must play a different decision pi star of G for most of the time if the true instance is G. This means that every consistent algorithm have a different behavior on F and G, so it distinguishes G from F. If the algorithm fails to distinguish F and G, meaning that it will play the same decision on both F and G, then we will have a linear regret on at least one of these instances. Therefore, every consistent algorithm must distinguish F and G with probability something like 1 over n. So if you only distinguish with a probability, say 1 over square root n, you will have a square root n regret. Okay, and how do we measure the distinguishability? So we measure the distinguishability in this paper by KL divergence. And this result traces back to the very classical result on hypothesis testing. This is called the Chernoff-Stein lemma. When written in our language, the statement of the lemma is as follows. So given a sequence of decisions pi1 through pi m, and the corresponding observations O1 through Om, then for every failure probability delta bigger than 0, the following statements are equivalent under mild assumptions. So the first statement says that there is an estimator that distinguish F and G in the sense that when the corresponding observations are drawn from the distribution introduced by F, this estimator will output F with high probability. So the probability goes to 1. It's like 1 minus small o of 1. And when the corresponding observations are drawn from the instance G, this estimator will output G with high probability. So the failure probability here is smaller than delta. And this lemma says that this distinguishability is equivalent to that the expected KL divergence between F and G is bigger than log 1 over delta. So in our setting, we call that we need a failure probability on the order of 1 over n. So this means our expected KL divergence should be at least log n. And we can rewrite this expected KL divergence in the following way. So we first take a sum over the decision, and we introduce a weight, W of pi, and then times the KL divergence of the distribution introduced by the decision pi on F and G. Here, the weight, W of pi, is just the expected number of times we execute a decision pi. And this is the unnormalized frequency of executing a decision pi. Okay, so finally, our complex measure is a kind of a optimization problem that tries to find the best frequency of decisions. So we have two conditions for the frequency. So first, we want to minimize the regret. Then we want to collect enough information to distinguish f and g, because every consistent algorithm must distinguish f and g. So we write the following optimization problem where the variables being optimized is the frequency w, and the objective here is just the expected regret if we execute this frequency of policies, frequency of decisions. And our first constraint here is on the KL divergence between f and g for every other instance g with a different optimal decision. And we also introduced this technical constraint here, saying that the frequency should be at most n. And then our final complex measure, C of f, is defined to be the limit of this optimization problem, C of f and n, when n approaches infinity. Okay, so the main difference between our complex measure and the complex measure in prior work is that we add this constraint that the frequency is smaller than n. So intuitively, this is saying that we can only execute each decision at most n times if we only have n rounds of interaction. And this constraint is to ensure mathematical rigor, because without this, the optimal solution could take the value positive infinity. And but for like some well-behaved hypothesis class, say the regular multi-arm bandit, linear bandit, this constraint doesn't matter, because in those cases, the limit equals exactly C of f infinity. This is the optimization problem without this constraint. But to extend to general interactive decision-making problems with arbitrary hypothesis class, we need to add this constraint because it is possible that this limit doesn't equal to the optimization problem without this constraint.
Can I ask a question?
Yeah, sure.
On the previous slide, you said you can distinguish f from g under any policy, or so the condition is so whatever policy you apply, f and g can be distinguished. Is that right?
So yeah, in this slide, we say we can distinguish f and g if we execute the frequency of policy given by w. So it's like we execute a sequence of policies, and we use the corresponding observations to distinguish f and g.
And this should be true for any pi 1 through pi m.
So the idea is that we want to find a sequence of policies pi 1 through pi m that can distinguish f and g. Does that make sense?
I see.
Not any.
Okay.
I had a
Go ahead.
yeah. Go back. Sorry.
Go ahead, Saba. That's fine.
Yeah, I had a related question for the lemma, just clarifying the statement of the lemma. Does this say like any fixed sequence of decisions, and is it talking about a fixed sequence of decisions, or is it talking about like sequentially chosen decisions?
It could be a martingale.
Yeah, it's like the sequential case. Yeah. Okay. That was my understanding. It was just like reading it. It was not clear. Okay.
Oh, yeah.
So if I can just ask this question, suppose f and g behave identically under pi, then their KL divergence will be 0.
Yes.
And then you're saying that you cannot distinguish f from g in that case.
Yes.
Okay. All right. Okay.
Okay.
Okay. Thank you.
Yeah, thanks for the questions. So yeah, let's move on. Now that we have defined the complex measure C of f, we can state our lower bound here. So this is saying for every instance, the regret of every consistent algorithm must be, when divided by log n, must be bigger than C of f. And I think this proof is very similar to that of prior works. And the complex measure C of f recovers the instance optimal bounds for multi-element bandits and linear bandits, and it improves the instance dependent bounds for tabular reinforcement learning. I think there are actually two ways to see this. So one way is that we can explicitly compute the value of C of f on the multi-element bandit and linear bandit instances and directly compute that value with prior works. Or we can argue that this complex measure for instance optimal bounds must be unique. This is because all the instance optimal algorithms are consistent. So by definition, they're as good. Their regret bound is as good as each other. So this complex measure should be the same. Okay. That's everything for the lower bound. Let's now move on to instance optimal algorithms we designed. So the idea of our algorithm is exactly the same as the one we designed, the lower bound. So we just want to collect samples with the best trade-off between incurring minimal regret on F and distinguish G from F. Now, this distinguishability is exactly on the hypothesis testing problem. So on the very high level, we essentially reduce the problem to hypothesis testing with active data collection. Okay, recall that our goal here is to show that the asymptotic regret of our algorithm is smaller than C of f times log n. So we are free to throw away every low order terms. Our algorithm here is called test to commit, or T2C. It is a three-step algorithm. So in the first step, we do some initialization. We first explore uniformly for small o of log n steps. And then we run the MLE estimator to get an estimation of the true instance called f hat. Now this step, because it only runs small o of log n steps, the regret is a low order term, so it can be thrown away. Now the second step is called identification. And in this step, we compute the best frequency W of pi by solving the optimization problem C of f hat. And then we collect theta of log n samples correspondingly. Now, the leading term of the regret comes from step 2, because in this step, we just collect theta log n samples. And with all these samples, we just run a hypothesis testing method, and we ask whether our estimation f hat is the true instance. Then we move on to step 3, called exploitation. So in this step, if our original estimation f hat is accepted by the log likelihood ratio test, then we just commit to the optimal decision of f hat. We run that decision forever. Otherwise, if the f hat is rejected by the hypothesis testing, we just simply give up and run UCB. And I would like to mention that our three-step algorithm is inspired by this very nice prior work that works on asymptotic instance optimal algorithm for linear bandits. Okay, as we see before, so the key step here is the identification, because in this step, we introduce our leading term of the regret. So first of all, why do we need this step? This is because our estimation f hat in step 1 is not accurate enough for us to commit to a fixed decision. So with only small o of log n samples, the failure probability is at least inverse polynomial in n. This is because typically to get a failure probability delta, you need something like log 1 over delta samples. So to get a failure probability 1 over n, we need log n samples. Therefore, in the second step, we boost the failure probability to 1 over n via hypothesis testing. We do this by solving the optimization problem C of f hat log n to the power 1 over 4 to get a frequency of the decisions. And then for each decision pi, we run it for w pi times log n runs. So recall that the second parameter here gives an upper bound on the value of the w pi. So in this step, we will incur C of f times log n plus some low order term, regret. And meanwhile, we also get enough information in the sense that the KL divergence between f hat and g is larger than log n for every g with a different optimal decision. This is guaranteed by the definition of our optimization problem. Now, with all the samples we collected, we can run the log likelihood ratio test on f hat. So we define the following event E of f hat to be the event that for every other instance G with a different optimal decision, the log likelihood ratio between f and G on the observations, on the empirical observations O of I is bigger than log n. Here we choose log likelihood ratio test because it is one of the optimal hypothesis testing methods. And okay, by the Chernoff-Stein lemma, we can get the following guarantees for the second step. Here, for simplicity, we just assume that our hypothesis class is finite, and we can extend to infinite hypothesis class later. So the first guarantee is that when our estimation f hat is indeed correct, then we accept f hat, our estimation, with a very high probability. So the probability is 1 minus small o of 1 times the size of the hypothesis. This is because we need to do a union bound on every other instance G. And because the hypothesis is finite, so capital F has a constant size, this is actually, so this failure probability goes to 0 when n goes to infinity. Now, the second guarantee is that if our estimation is way off, in the sense that it has a different optimal decision than the true instance, then we will reject this estimation with very high confidence. So the probability that a wrong estimation passes the test is upper bounded by 1 over n. Okay, finally, we can put everything together to get a regret upper bound for our algorithm. So in step 1, we can show that our estimation is accurate in the sense that f hat exactly equals to f with probability at least 1 minus 1 over log n. This guarantee is not surprising because we have a uniform convergence result for the MLE estimators. So basically, it says that in order to achieve failure probability delta, we only need something like O of log 1 over delta samples for MLE estimators. Here, we only need a failure probability 1 over log n. So in principle, we only need log n samples. But in step 1, we allow anything small o of log n samples. So we are good here. Then in the following, we just do some case analysis. In the first case where our estimation is accurate, the second step will have regret C of f log n. And in the third step, if this estimation passes the log likelihood ratio test, we will have 0 regret. Otherwise, we run UCB forever, so we have log n regret. But the probability of f hat that were rejected by the hypothesis testing goes to infinity. Sorry, goes to 0. So in this case, the expected regret is a low order term, so we can safely throw that away. And in the second case, where our initial estimation is not correct, the step 2 will have a regret with something like log n times log n to the power of 1 over 4. This is because we have upper bound for the frequency as a second parameter in our optimization problem. In this case, we choose log n to the power of 1 over 4. But since this case only happens with probability 1 over log n, so the expected regret in this case is also a low order term, and it can be thrown away. Now, in step 3, we will have a linear regret when f hat has a different optimal decision as f. But in this case, by the second guarantee of the log likelihood ratio test, the probability is extremely small. It's like 1 over n. So the expected regret is also a low order term. Otherwise, we run UCB, so we have log n regret, and that's good. To put everything together, the overall expected regret is given by the regret of the second step, which is C of f times log n plus some low order term. Okay, so finally, we can prove this upper bound, saying that the regret of our algorithm T2C divided by log n is asymptotically smaller than C of f. When instantiated on tabular episodic reinforcement learning, our algorithm is the first instance optimal algorithm. Okay, this is the analysis for our algorithm. I'll pause for questions here for a little bit.
Yeah, I don't know. I have a high level question. So there was this Graves and Loy paper, or Loy Graves paper, that had a lot of the ingredients of these ideas, right? Like, how do you, like, can you remind us how this compares to those results?
Yeah, sure. So I think their complex measure is very similar to ours, but their analysis was written for ergodic Markov decision processes, meaning that for every decision, for every policy, you will have a positive probability of visiting every state if you run that policy forever. So in that case, the exploration is less of an issue because you will eventually visit every state. But here, our algorithm or our analysis works for general interactive decision-making problem, including episodic reinforcement learning. So we need to explicitly compute the best trade-off between exploration and exploitation. Does that make sense?
Sure.
Okay, sounds good. Thanks for the question. All right. Now let me briefly. Oh yeah, sure. Go ahead.
Yeah. So I had a question about the interactive nature of the algorithm. One thing that we can expect when we have ability to act upon interactions is that we can accommodate any uncertainties that are going on. For example, if we take an aircraft taking off, the taking off part has a different dynamics than the aircraft just cruising, right? So would the policies, would we be able to identify what instances are optimal on the fly? Or rather, would we be able to make a switch between the choice based on the interaction, like midway through an episode or something like that?
Oh, sure. That's a good one. Thanks for the question. So I should mention that our algorithm, this 3-step algorithm is particularly designed for better exposition. So in this case, we don't have this the set of the frequency of the policies is not iteratively refined. So we just do one round of initialization, identification, and exploitation. So in this case, we
so
just fix.
We can switch,
Sorry,
but we cannot tune, right? Here we can switch, but we don't tune, right?
Right. We don't tune this frequency.
Okay.
I think an equivalent way of stating this algorithm is to selectively change step 3. So if f hat doesn't pass the test, we can just go back to step 1 and run this all over again. In that sense, we can tune this frequency w pi again by rerun this initialization phase.
Okay, so we are going
and that
to,
one will give you the same theoretical guarantees.
Okay, so we're going to eliminate the bad ones at step 3 iteratively.
Yep.
Okay. Thank you.
Yeah, thanks for the question. Okay. Now let me briefly talk about how to extend to infinite hypothesis setting. So the difference in step 1 is that first of all, there are 2 differences. We need to change the analysis for step 1 and step 2. So in step 1, when we do initialization, we cannot expect to find the exact optimal, the exact true instance because we have infinite hypothesis class. So in step 1, we just need to prove that our initial guess f hat is close to the true instance f with a probability 1 minus small o of 1. So we need, in particular, we need the following guarantees. So the first one is that our initial guess has the same optimal policy as the true instance. Second one is that the solution of the complex measure on the initial guess is close to the solution on the true instance f hat. The true instance f. And the third one is that our initial guess can pass the log likelihood ratio test. So essentially, this is just saying we need the KL between f hat and g is close to the KL between the true instance f and g for every other instance g. Okay, and the other difference is in step 2. So in this case, we just need a small covering number for the hypothesis class to prove a uniform concentration, result. And the algorithm stays exactly the same. We only need to change the analysis. All right. So let me finish by talking about some takeaways. So first of all, we through this algorithmic framework, we show that instance optimality can be achieved by hypothesis testing with active data collection. So the key step here is to find the best trade-off between collecting information and incurring minimum regret. Also, this abstraction of interactive decision-making framework helps simplify the analysis. So we abstract away the actual structure of the problem into a single random variable called observation, and we only need some classical assumptions, say the uniform convergence, on the distribution of the observations. Finally, there are lots of remaining open questions on the line of instance optimality analysis. So first, we can try to improve the T2C algorithm. Our algorithm is particularly designed for simple exposition. So there are a lot of remaining open questions there. For example, we can look at the computational efficiency of our algorithm on concrete settings. And we can also look at instance optimality for the cases where we have infinite decisions. And lastly, we can look at the non-asymptotic performance of the T2C algorithm. This is because in our algorithm, in our analysis, we just directly throw away all the low order terms. But if we analyze that carefully, the low order term will be growing like linear to the side of the decision space. And that is not acceptable if you only have a small number of interactions. And I would like to mention this follow-up work. This is a very nice follow-up work on the non-asymptotic performance of interactive decision making. So basically, they improve the low order term significantly and make it like polynomial in the problem dimension. Okay, on a higher level, we can look at the instance optimality for other questions. Say, we can look at instance optimality for sample complexity instead of regret. And we can look at, say, offline RL instead of online reinforcement learning. And we can also look at instance optimality for supervised learning. Say we have a classification problem, we want to have instance optimal algorithm. And some difficulties there is that we need to first find a concise way to define consistent algorithms. And then, of course, the first question to ask is always the existence of instance optimal algorithms. We have some preliminary studies here. So for offline RL, the existence depends very much on the way you define consistent algorithms. So in some definition, there doesn't exist instance optimal algorithms, but for some other definitions, we have instance optimal algorithms. Okay, that's everything for today. Thank you for your attention, and questions are welcome. Thanks.
Thank you.
So I have a question again about the non-asymptotic results by Andrew and Dylan there. So is there any advantage of this T2C algorithm to theirs? Does it obtain any better results than theirs? Because from what I understood, you were saying that theirs has the same leading order term and then just better lower order terms. So is that one strictly better than yours?
Yes, in terms of the result, yes. I think that one. I think it's a follow-up work. It comes like a few like 1 year later. But yeah, their algorithm's really nice, and I think one advantage of our algorithm is the conceptual simplicity or the analysis perspective. So we just focus on the high-level ideas of instance optimality analysis.
Yeah, thank you.
Yeah, I do have a question about this uniqueness assumption. So there was the assumption that the unique optimal hypothesis. So basically, the lower bound applies to instances that have a unique optimal hypothesis. I'm thinking about MDPs. You have a lot of symmetries. Let's say you're in a grid world and like so many solutions, so many hypotheses that give you the same value. So that seems like a bit of a restriction. So have you thought about what's going on there if you have multiple optimal policies?
Yes, that's a good question. So I think the main difficulty there is in the definition of the complexity measure. So recall that our constraint is that for every other instance with a different optimal decision, you need to have the KL divergence bound. But if you have optimal policy, there are multiple cases, right? Say if the other instance have like two optimal decisions and one is also optimal in the true instance, then for the lower bound part, we do not need to distinguish these two instances. But from the upper bound perspective, we do need to distinguish these two instances, because if you happen to have the other instance in your first step in the initialization, which has two optimal policy, then you do not know which one to commit to in the third step. So there's this gap there. Yeah, I think it needs some further analysis to drop that assumption.
Is it going to increase the lower bound? What do you expect? Are these easier instances or harder instances if you have duplicates? And actually, it's interesting. You can have a duplicate on the instance that you're considering, and you can have duplicates on the alternative instances. Both are problematic for various reasons.
Right. I think if you have a instance, if you have an instance with multiple optimal decisions, that is not the one you considered. We can only prove a smaller lower bound, but a bigger upper bound. So there will be a gap in between.
Right.
Right, because you have less.
Yeah, I guess I was curious about what do you feel? What's the truth? Is it going to be the upper bound or the lower bound? In this case, usually I bet on the lower bound, but in this case, I'm not sure. Seems the lower bound is missing something there.
I would guess both. I mean, at least we have to. Yeah, at least we have to change the definition of the complexity measure.
Sure.
Yeah, and I think we also need to do more in our algorithm.
Sure. Okay.
Yeah.
I guess it seems like the lower bound may increase because you're confounded. You don't know whether these two policies are really different or they're the same. And that's why you have to invest more to separate them.
Yep.
Yeah. I would think so. Yeah, that will be curious. And related, what about infinite action spaces? What do we do there?
Yeah, so that's a little bit tricky because so recall that in our lower bound we say we need to distinguish two instances. But if you have a infinite action space, it's not always the case. You can have a instance that is arbitrarily close to the true one. So it's unclear whether you need to distinguish that.
Yeah.
So if you fix one instance and let n goes to infinity, of course you need to distinguish different instance. But yeah, I think there's something happening there that prevent our analysis to the infinite decision space.
I mean, like the regret rate could be radically different too. It's like not log regret anymore because it's not discrete.
Oh. Yes, that will also be possible. Yeah.
Yeah. Asymptotically.
That's a good question.
Yeah. And regarding MDPs, so if you would just take an MDP and like you would try to evaluate your metric, like does it give some interesting insight into what the heck is going on, or have you thought about this?
Oh yeah, I think there's a very nice prior work on this. That studies the some sort of complex measure that is very similar to us. So basically, you just drop the constraint on the infinity norm of the frequency, and yeah, in that paper, I think they have some intuitive.
Which paper is this?
Wait, let me find that. I think it's called. that paper mostly focused on the lower bound part. Sorry, 1 second. This paper is by Andrea Tirizzoni. This is called a fully problem-dependent regret lower bound for finite horizon Markov decision processes. Yeah, so they have some intuitive, like some solutions. They computed some kind of closed form solutions to a complexity measure that is very similar to ours. So basically what happens there is that you just look at, so they prove that the hardest instance that you need to distinguish from can only change one the state the transition on one state. So you just need to look at a small subset of the instance to compute the optimal value. Sorry, just to compute the complexity measure. It's kind of similar to inverse gap stuff. Yeah. The final form is kind of similar to inverse gap.
There was also this paper from 90s by Burnets and Katakis, right? That was also studying the continuum case or the average reward case. Like, what's the relationship between that lower bound and the lower bound that you would get?
I think
that's somewhat different because it's continuum setting, right? Like, is that going to make a difference?
So I would say that if you only consider the standard hypothesis class for tabular reinforcement learning, all of the lower bounds will look very similar, or like equivalent. Yeah, that's my feeling. Yeah.
If we're talking about the same quantity, then sure, like they have to be the same, right?
Yeah. That's.
Or there is a bug somewhere. But sometimes they are expressed analytically differently, right? Like different optimization problem, different looking optimization problem, but it should give you the same results. But sometimes even the problem classes are slightly different. Like the Bunes-Kateha case is for the average reward case, and I think that there is some restriction on the supports of the next state distributions as well.
And yeah, to add on that, I think if you have an ergodic Markov decision process, you can explicitly compute this complexity measure. It's also like inverse gap, a summation of inverse gap on state action.
Yeah. Okay. Yeah. I see. Action gap. Yeah. I guess. Action value gap. Right. Yeah. Okay.